Most technology education today looks exactly like this. A weekend coding camp here, a standalone robotics kit there. Students play with these tech toys, but they eventually hit a wall. There is rarely a continuous path connecting those fragmented weekend projects to actual engineering, which raises a difficult logistical question. How do you teach subjects like ethical hacking or artificial intelligence to a 5-year-old without overwhelming them? The solution involves replacing isolated camps with a structured architecture. WCode designed a comprehensive end-to-end curriculum mapping this entire process. This map illustrates 13 years of development, 4 divisions, 12 ranks, and 48 badges across 7 domains. The strict rule for early years is to establish the mental model of logic first, entirely avoiding programming syntax. Producing a highly capable engineer requires a continuous blueprint, building skill upon skill, rather than hoping a random assortment of tech gimmicks will stick. That blueprint begins with Phase 1, Early Makers. For ages 5 to 7, the curriculum enforces an absolute ban on text-based code. Instead, students use physical logic tools, like the Code and Go robot mouse and the logical road builder. They learn multi-step sequencing, debugging, and spatial reasoning by physically moving objects across a table. By age 7, those spatial concepts scale up. Students design their own custom objects in a browser using Tinkercad, and then have them 3D printed in-house. Then comes Phase 2, Junior Innovators, spanning ages 8 to 10. This is the structural bridge where block-based concepts convert into actual text. Students take the exact visual blocks they used in MakeCode and rewrite those same projects into MicroPython to run a microbit microcontroller. They apply this logic to machine learning, using tablet cameras to train their first working image classifiers with 3 distinct categories. These foundational skills are immediately pushed into the physical environment, as students program Codrone EDUs to fly manual obstacle courses using Blockly commands. By steadily substituting physical toys with strict text-based syntax, the curriculum transforms abstract childhood play into a concrete engineering discipline. In Phase 3, Middle Explorers, the training wheels come off. For 11 to 13-year-olds, every tool must produce a functional, real-world output. In web development, students write HTML, CSS, and JavaScript to launch live, responsive, multi-page portfolio websites to public URLs. Cybersecurity training accelerates from basic digital safety lessons into guided, hands-on capture-the-flag network defense exercises. Hardware programming scales up as well. Students write Python algorithms for Zoomy cars, using IR sensors and computer vision to navigate custom autonomous routes. This sets the stage for the final phase, Teen Visionaries. From age 14 to 18, students operate exclusively within professional-grade environments. They integrate OpenCV computer vision libraries with their drones, programming them to autonomously map and track specific visual targets in midair. They build and deploy custom neural networks and configure single-board computers like Raspberry Pis to host their own local servers. The stakes become entirely real. Using Kali Linux, students run penetration tests to discover and submit valid vulnerabilities to actual bug bounty programs like HackerOne. The objective of these final years is to stop running simulated sandbox scenarios and start actively manipulating real-world digital infrastructure. Looking at this timeline, the 17-year-old deploying a full-stack web application on the right is the same student who learned sequencing by pressing buttons on a plastic mouse on the far left. This compounding growth happens simultaneously across drone programming, 3D printing, artificial intelligence, and all 7 domains of the curriculum. True technical fluency is not a byproduct of raw talent. It is the result of a 13-year progression where every skill builds directly on the last. Graduates exit the program with a professional portfolio, including active GitHub repositories, live API endpoints, and business pitches for multi-part 3D printed products. They also complete a mandatory capstone project, assembling cross-domain teams to solve specific, real-world problems for local organizations. By engineering a 13-year compounding roadmap, WeCode provides students with the specific technical infrastructure required to build the future.